experiment is getting much affected because of this corona. Means the time went wrong. That means we wanted to start things at the time, and then if the physically students, postdoc cannot come in the campus, how can experiment be done?
Yeah, exactly. See, we have students here, but because of this condition of 2 per lab, try to avoid. Many of them are in the hospital. I have not seen them.
Yeah, but we called them, and then exponentially corona infection happens, and then it's stopped. And now they have, means initially they were allowing PhD student and postdoc only, but then they stopped those also. Means now only emergency staff can come in the campus. And hostel is completely closed. So if we invite a postdoc, he can come, but then the hostel is not available.
Yeah. See, I'm also scared to invite people if something goes wrong.
So I stopped them for a while. Means they were here. Means they were not going home. But then the thing was increasing like anything.
Yes. Like this, Subimal has joined here.
Where?
Subimal Dev. He has joined here in that array. That array 3.
Oh, okay.
First array 3 project.
And your DRDO thing will also start soon.
So Chiranjeev, we can start, Chiranjeev.
ठीक है, we'll start. Okay. Welcome everybody. We are very honored to have Professor Anirban Pathak from JP Institute in Noida. Both Professor Panigay and I have known Anirban for a long time because from the time we started working on quantum information in India. So Anirban has been one of the original contributors and one of the first person to start the field in our country. So Anirban graduated did his PhD from Vishwabharat in Shantiniketan, and then he was a postdoctoral fellow in Freie University, Berlin, and then he joined JP Institute in Noida in the year 2002. And Anirban has got a lot of accolades, published a lot of papers in quantum optics, quantum information, and quantum cryptography. And he has also been teaching these subjects in JP Institute for a long time. So he has graduated numerous amounts of PhD students and also a large number of postdoctoral fellows. So some of the accolades, to mention some of the accolades, Anirban is a fellow of the National Academy of Sciences in India, and also Institute of Electronics and Telecommunication Engineering, Optical Society of India. So in the year 2007, Anirban was awarded Sri O.P. Vasin Award in the field of electronics and information technology. So without further ado, I would just hand over the ground to Anirban, and he's going to talk about his field. Thank you, Anirban.
So thank you, Chiranjeev, for the introduction, and I would also like to thank Chiranjeev and Professor Panigay for inviting me, and especially for arranging this, which is giving an opportunity to many young students to learn about the field. So although the meeting is now about 2 weeks old, because it started from 14th of June, but since there are many MSc students are attending and all are not expert, so I'll keep the talk a bit lucid, so that everyone can follow. And still, if at a point you feel that something is not clear, you stop me there itself. Don't wait for the 1 hour talk and then only in the last 30 minutes you can ask me. It's not like that. If you feel in between that you want to ask something, you can feel free to ask. But it's more important that the points are clear than to follow the protocol for 1 hour and then we start asking questions after 1 hour. So this slide, the beginning slide is showing some pictures. So in one picture, you can see that in Google, the quantum computer is shown, and they achieve some quantum advantage. That's what they claimed. And it appears that the quantum computer is very big, but most of it is cooling device. So all the things which you see outside, they are cooling because, and why they are cooling? Because quantum states are very unstable. You cannot keep them in normal temperature. So actual quantum computer can be like this. So in the right hand side, you can see a CHHBr molecule. So this was a 3-qubit quantum computer in NMR implementation. So there are different kind of implementations. So IBM and Google's implementations are superconductive, and so in superconductive quantum computers, means most of the quantum computers which you can access through cloud are superconducting in nature. Say, for example, IBM Quantum Experience give you access to the IBM's quantum computer shown below, and this is the quantum computer of Google. Means everywhere there is the cooling part is much bigger, and actual computer is like a chip. Now, so why we are talking about these quantum computers? Because they are important for our security purpose also, because unless a big quantum computer is really made, the classical cryptography is not in threat. So quantum cryptography will not have a market. So why is it so? I'll come back to that. Then you see that this is in the extreme right corner, there is a optical processing. So optical quantum computers are also or photonic quantum computers are also proposed, but they're not good candidate for making quantum computer. So from all these pictures, you can see that from NMR, from superconductivity, so transmon qubits, there are many implementations of qubit. But when it comes to communication, you have to send a qubit from one place to other place, then probably the photonic is the only alternative, because you cannot send a molecule from one place to another place very easily. So photonic implementations are more important for secure communication, but security is needed for computation as well. So security, as the title suggests, the notion of security in the quantum world, advantages, expectation, and challenges. So the notion of security will not only affect the computation, communication, it will be connected to metrology also. So we'll gradually come to that. And then in the extreme right corner, I show a pillar. So this is a pilgrimage for all cryptographers. So this is in Poznan, Poland, and there is a triangular pillar and 3 names are written. Those are the 3 peoples who broke Enigma, Hitler's code. And so code breaking is also a very important part. So apparently quantum cryptography is unconditionally secure. So that leads to a question whether the code breakers like Rejowski is still relevant. The answer is yes. And at the end of the talk, I'll come to those ideas which can be used for code breaking. So anyone has an idea that how to remove this lower part, which is blocking part of the slide? Okay. So this is where we are showing some achievements and which lead to the expectations. So this is a Soccer World Cup 2010, and the football ground was connected with quantum cryptographic link, and the players' movement data was encrypted using BB84 protocol of quantum cryptography. The next one is showing the satellite-based link between Austria and China, and there was a satellite, and the satellite established a key with China, another key with. So I'm coming back to that, but this was the longest communication using quantum resources. So quantum resources was actually established the key, and then using that key between 2 continents, a video conference was possible, encrypted video conference. The ITQ Clavis is shown. This is a quantum product which is providing commercial quantum cryptographic solution, and we show some quantum computers, D-Wave, IBM's 5-qubit quantum computer, Rigetti. So Rigetti and D-Wave you can access from Amazon Web Services, and all these are connected to security, and gradually things will be clear. And there are some questions which were not much relevant 2 years back or 4 years back when IBM or AWS, etc. were not available, which are relevant to security. Those are of delegated quantum computing. So what does it mean? So you see, you have a laptop. Your laptop is classical, or you have a mobile phone, which is classical. But using your mobile or laptop, you can access IBM's quantum computer. Now you can throw a job in IBM's quantum computer. How will you know that IBM is really doing it a quantum computing? IBM is not taking your job and running it in a large classical computer and returning it to you. Then, if the quantum computer becomes a little bigger and you buy a slot in IBM, so IBM is just doing computation for you. So you are delegating the job. So when you are delegating, you will expect that IBM will do the job or Rigetti will do the job for you without knowing what he is computing. So he must be blind. So you want to maintain privacy. You want the quantum computer to be blind and do the job in quantum computing, and you want to check the answer as well. So can you do those things using a classical computer? So when you are throwing it from, you don't have the big resource. The quantum computers will be in cloud and then you are from somewhere else. So how will you maintain privacy? So whether delegated blind computing is possible or not, these questions were not relevant few years back. But with the introduction of this kind of services, which is provided by AWS or Quantum Experience, these new questions related to security appeared, and we'll come back to that. Finally, here is a quantum radar. So quantum radar, the China claimed that they have already made the quantum radar, but US claimed that they have made much progress, and it means the main goal of it is to find out the stealth aircrafts. So this is not a security in the nature of computation and communication. This is more like metrology. So several things are part of quantum metrology, which will also affect the concept of security in a broader sense. So one such thing is that when gravitational detectors can be built, so quantum detectors can detect a kind of map of gravitation. So what will be its effect? So you see, if there is a submarine and I can map that in which part there is how much gravity. So submarines, the mass is not distributed uniformly. So in some place there is more mass, some place there is less mass. So I'll have a mass map, just like a thermal image, I will have a mass image. And when I have a mass image, I'll be able to detect submarine. So this will be affecting the balance of power in many sense, the notion of security from military sense. Why? Because now if somebody has 2 submarines and his enemy or neighbor has 10 submarines, they are more or less equally powerful because nobody knows where those 10 submarines are placed or where those 2 submarines are placed. But the moment I will know that my enemy has 1 submarine and that's in particular place, then I can attack the country from some other end. So a kind of disbalance in the power among the countries which has submarines will appear, and the countries which has more submarines will become more powerful, or the country who has a gravitational detector will become more powerful. So notion of security in a broader sense will change massively in the quantum world, and which is not restricted to quantum cryptography only. And understanding this need, the expectation is changing, and people are doing many things. So here is an article from Washington Post. So US plans to build a quantum internet that might be unhackable, and many people are trying, but there are certain concerns about the security of quantum networks. So first we'll understand QKD, and then I'll mention that what is the problem with the quantum network. So at least I can briefly tell you that if you can do quantum cryptography and establish that between Calcutta and Delhi, there is a secure link, and between Delhi and Bombay, there is a secure link, but that does not mean the link between Kolkata to Bombay is also secure. So point A to B is secure, B to C is secure, does not mean A to C is secure. So if such security proof can be provided, then it's called composable. So in the network, there may be 2 people. I'm using BB84 protocol to establish a link with you, and you are applying B92 protocol for establishing a link with your friend. So if your link is epsilon1 secure and my link is epsilon2 secure, and the combination is epsilon1 plus epsilon2 secure, then it will be called composable. So composable security is the need of the time. Then there are other issues, but gradually we are promoting ourselves from two-user scenario to multi-user scenario, and different protocols are proposed. Proof of principle experiments are done. Some network is also created. And people are looking for real quantum internet. So far what we have is more or less point-to-point quantum communication, but gradually we are moving towards quantum internet or quantum network. So this slide gives a kind of glimpse that what we do in context of secure quantum communication. So there are not only QKT, there is something called QKA, where both the users agree on the key and both contribute equally to each bit of the key. There's something called quantum dialogue, which allows both parties to talk using quantum resources. So a special case of quantum dialogue is only one person speaks and other person listens in the secure manner. That's called quantum secure direct communication. So what is the difference with QKD? In QKD, first you have to generate a key using quantum resources, and then you use classical means to say you have a message which is 0010 something, and then you have a key of the same length. You do bitwise XOR and send the result. And then somebody else has the key. He does bitwise XOR. So you have message XOR key, and then the other person is doing message XOR key XOR key. So key XOR key is 0, so that cancel and he gets the message. So that's a classical means, but you generate the key quantum mechanically and then you do that. And there is a principle called Kraushoff's principle, which tells that if the key is secure, then your cryptography is secure. So all the efforts is primarily directed in generating and distributing quantum key, but it's not limited to that. There are protocols which show that you can directly do secure communication without taking a key, and that has two kind of things. One is discrete deterministic secure quantum communication, where to decrypt the message you need some additional information, and in QSDC you don't need that. That's quantum secure direct communication. Now both of them have control version. So why are we interested in control version? Because in control version there is a controller who is a third party. So the appearance of controller makes it that Charlie, the controller, can control that how much information Alice and Bob can communicate, and they can communicate in a secure manner. And that becomes very relevant for online shopping kind of stuff. Suppose you want to buy something from Big Bazaar, but how to pay? So you have to contact your bank. So once you contact your bank that I want to buy something from Big Bazaar, the bank will generate some photons or some qubits, share it between you and Big Bazaar. You give your authentication and Big Bazaar gave his authentication. Once bank verified that both are authenticated users, then bank will allow the transactions. And you will send a list of things you want to buy from Big Bazaar, and Big Bazaar will send the amount requested. Bank will ask you, do you want to pay? And when you agree, after authentication of the users, bank will send the amount to Big Bazaar. So that's a three-party protocol where the transactions is controlled in a secure manner by the bank. So that's kind of control quantum secure direct communication protocol. So in principle, in one of our work, we have shown that every protocol of control secure direct communications can be modified to quantum e-commerce. So quantum e-commerce or online shopping. So these are more practical things, and these are not really communication, these are computation. And there are other works on computations which makes it relevant. So for example, voting, auction, socialist millionaire problem, e-commerce. These are some problems which we are interested in, which are computation. So the message is that not only communication, computations, and in the traditional sense, military security is also affected in the quantum world. There are some problems which people know that does not exist a quantum repeater. There is no quantum memory. Quantum secure direct communication and such protocols require quantum memory. So you will often see that experimental papers are appearing. So instead of quantum memory, what they are doing is actually using quantum delay. So there is a difference between a delay and a memory. So you put in a fiber and the photon can come out after 3 milliseconds or 3 microseconds, whatever waiting time you want. But then the second photon will come after same time. So if you decide in between that I know the third qubit first and then the second qubit and then the first qubit, it will not work in that way. Whatever delay you have pre-decided, it will come out after that delay. So there is a basic difference between delay and memory, since memory is not really available. So in the most of the experiments, delay is used. Often people use something called POP. So this is called particle order permutation. So you have a set of Bell states, say, and you decide that order will be permuted. So the first qubit will come, say, when it comes in sequence, then it may be that first qubit is entangled with the 37th qubit, second qubit is entangled with qubit number 13, qubit number 3 may be entangled with qubit number 5. So Eve does not know that which one is entangled with which one, and if it chooses incorrectly, then it will lead to something called entanglement swapping. And then when all these qubits will reach to Bob, and Bob will confirm that I have received all the qubits sent by Alice. Alice will disclose the position of some of the qubits, the coordinates, in the sense that, well, for checking that first is entangled with third, fourth is entangled with, say, 67, and Bob will take those and do a Bell measurement, and they should be in the same state, same Bell state as Alice has sent. If not, that means Eve is doing something. And then if there is Eve, then Alice will not disclose that what was his encoding or what is the coordinate of rest of the Bell states, that which particle is entangled with which one. So this kind of things, that ignorance of Eve about which qubit is entangled to which one, leads to change in the state when it is measured, leads to security in quantum communication. So where from the security is coming? So when you are sending this Bell states, so if you do a measurement in Bell basis, it will be always in Bell state. But you don't know which qubit is entangled to which qubit. So Eve become ignorant about the spatial basis. So what is a spatial basis? Quantum mechanics is probabilistic, but there is a difference in the sense of probability in quantum mechanics, and that's in the classical world. So if you measure a plus state in the plus minus basis, the state is suppose 1 by root 2 0 plus 1 by root 2 1, and you are measuring in plus minus basis, it will always be plus state. It will never be, but only when you choose a wrong basis, say you are measuring in 0 1 basis, then a plus state will be half of the times in 0 state, half of the time in 1 state, because it's 1 by root 2 0 plus 1 by root 2 1. So probability of getting it in 0 is half, probability of getting it in 1 is also half. But if you make it in plus state, it will always be plus. So if non-orthogonal states are there, non-orthogonal states cannot be in the same basis. So you don't have a unique choice of basis. So you cannot discriminate non-orthogonal states. But what about orthogonal states? Of course, you can measure and identify. But when I am changing these Bell states and changing their particle order, then Eve does not know. Eve knows that I have to do Bell measurement, but Eve does not know which particle is entangled with which one. So the spatial basis in which the probabilistic nature is missing, or it is deterministically you can identify the state, is not available to Eve. So that is the condition for getting quantum cryptography. So quantum cryptography is providing the security by exploiting laws of quantum mechanics or laws of nature. So it's exploiting that Eve cannot clone it. So that's no cloning theorem. It's exploiting uncertainty principle. So it is exploiting the laws of physics, non-results of quantum mechanics. But in contrast, classical cryptography exploits difficulty of a problem. So we'll come to that. But this POP, I told specifically because there is no optics technology which can allow you to do particle order permutation. So the optics for particle order permutation is not known, but this is often used in the protocol. All this protocol of quantum secure direct communication requires memory, but memory is not there. For long distance communication, you need repeater is not there. Single photon sources are required, but good quality single photon source on demand. So you can make a So often we use weak coherent pulses, which is an approximate single photon pulse, that you have a laser and you just attenuate it. So this is not available on demand, that I need a photon at 7 p.m. 30 microsecond. So photon will not come at 7 p.m. 30 microsecond. I can have a single photon, but it may come at plus minus 1 microsecond, say. So then there is a single photon detector's efficiency issue. So we have to detect single photons, but the single photon detectors are not very efficient. And the efficiency also depends on the wavelength. So whenever we do open air communication, we work in 800 nanometer or so, because there the detector is maximally efficient. But when you do fiber optic communication, then you work on 1550 nanometer because the fiber has less attenuation there. Now, we may require a hybrid kind of thing. Say you are doing a satellite-based quantum communication, but you will not be able to do it with Delhi and Calcutta. Why? Because the light pollution is extremely high. So you will not be able to detect the photon itself. So you have to do the satellite-based communication with a place which are relatively dark. And then if you get something and you have to bring it to Delhi or Kolkata, then you have to go for rest of the part in optical fiber. So you may require to transfer from one frequency range to another frequency range, and putting any trusted node is always prone to security risk. And then there are many attacks like detector mismatch attack, possibility of Trojan horse attack. So sometimes even the proposed protocol violate basic principle of cryptography. So what is the basic principle? That Eve can do anything which is allowed by nature. So Eve is not restricted by the technology, but Alice and Bob is restricted by the available technology. But often in the protocols, Alice and Bob go beyond this principle. Okay. So here is some basic ideas of quantum mechanics. Can I get rid of this strip on the top? Any suggestion means how to get rid of this? It's always blocking something.
We can see the slides fine.
Okay, so here is some basic ideas of quantum mechanics which I need. So for every physical observable, there is an operator, which I tell in every occasion. So you can see me, but I'm not observable because you cannot measure me. So anything that you can measure is a physical observable. For example, my mass is observable, my position is observable, my momentum is observable, and for them there are operators. So operator corresponds to physical observable Hermitian, and this is to satisfy that in a real experiment I get real eigenvalues. And that leads to the point that when we put it in Schrodinger equation, that the time evolution becomes unitary. The operator satisfies eigenvalue equations where eigenfunction of energy operator is actually called wave function, and eigenvalues are discrete values. So those are the values which a real experiment can find or can lead to. So time evolution of a quantum state is described by a unitary operator, but measurement operators are non-unitary and thus irreversible. And when you take care of noise, maybe somebody has already spoken, or the way it is taught in school, in classes, BSc classes or MSc classes, that you have a particle in a box, there is nothing on the world. You have a hydrogen atom and there is nothing in the world. But in reality, this is not the case. So it's not a closed system. The system interacts with everything surrounding it, and apart from the system, everything else is called environment. So when you take care of the environment, then we go to open quantum system. And when you solve your corresponding equations in open quantum systems, for different kind of model, you get different kind of models for noise and how you model the environment. So you get something called cross operators. So this is beyond this lecture to introduce those cross operators, but for modeling of noise, and noise is something real. So for modeling noise, you need cross operators, and those operators are not unitary. So measurement, but what is measurement operator? Suppose you have a state, a qubit, which is alpha ket0 plus beta ket1, and you want to project into state 0. So then the operator is ket0 bra 0. So similarly, operator for plus state will be ket plus, bra plus, ket minus, bra minus. And now I can see that if I write M0, which is ket 0, bra 0, and M plus, which is ket plus, bra plus, and take a commutation relation, this will not be equal to 0. Because the inner product between ket 0 and bra plus, inner product between 0 and plus, or the way you will write here is say bra 0 and ket plus is 1 by root 2. So that's not 0. So you will not get a 0 here. So Heisenberg's uncertainty principle tells you for any two observable, if the corresponding operators do not commute, you cannot measure them simultaneously with arbitrary accuracy. So this implies that if I have prepared some qubits in 0-1 basis and some are in plus minus basis, so I will not be able to measure them simultaneously with arbitrary accuracy. So either I have to measure in 0-1 basis or I have to measure in plus minus basis. So if I measure in 0-1 basis, a plus state will half probability become 0, with half probability it will become 1. So now this leads to something called BB84 protocol. We'll come to that. But you can see that we have an inability in measuring qubits in two different bases. And our realization is most of the times that 0 is a horizontally polarized photon, 1 is a vertically polarized photon, plus is 45 degree polarized, and 135 is minus is 135 degree polarized photon. There are some common operators, and you just need to remember H, operator for X, operator for E, etc. And if you write in Schrodinger time-dependent Schrodinger equation, Hi is equal to this, then you see that Zt is e to the power minus IHT. And since H is Hermitian, when you will take U dagger, H dagger will become H, and I will become minus I. So U dagger is U inverse, which is condition for unitarity. So here you see that the input J0 uniquely mapped to output Jt. So anything that can do that is called a quantum gate. So what is a quantum gate, or a gate which defines a map? A fixed input state will always go to a fixed output state. So if you fix a particular interaction H, so this is the interaction Hamiltonian H, and then you fix the time duration for which the interaction happens, then you have a specific gate. So that such a quantum gate is unitary, and since it is unitary, it is reversible. The filter. So neutral density filter creates attenuation, and then the photon comes. It's approximately a single photon. So I make the average photon number is equal to 0.1. Then most of the time there will not be any photon, but when there is a photon, there is one photon. So this is an approximate source. So the beauty of neutral density filter is that it reduces the average photon number, but keep the photon statistics unchanged. So if I have a single photon, and here is a beam splitter, which partly reflect, partly transmit. So before I do a measurement, the photon is reflected as well as transmitted. So this is the difference between the classical world and quantum world. So classically, photon will be either reflected or transmitted, but quantum mechanically, it is simultaneously reflected and transmitted both. So it is simultaneously in 0 and 1. But when I make a measurement, it will collapse to one of the possibilities. But before that, it's a qubit, because it is alpha ket 0 plus beta ket 1. So if it is a 50-50 beam splitter, it is 1 by root 2 reflected plus 1 by root 2 transmitted. So now, if I do put two detectors, and this detector clicks, then I call detector 0 clicks, I call it 0, detector 1 clicks, I call it detector 1. But at a given time, either the detector 0 will click or the detector 1 will click. So I will have a random sequence of 0 and 1. So this is what happens in a commercial product called Quantis, sold by ID Quanti. So this is the product. So in Quantis, and many casinos buy it, lottery companies buy it for ensuring that randomness is perfect. So there is a single attenuated laser source, a semiconductor laser, there is a beam splitter kind of things, and then there are two APDs inside a box, which looks like a charger of your laptop, or this can be a PCB card and inserted in your computer. But this is the most successful commercial product. Now, this randomness that on collapse on measurement, so there is a difference between your time and my time. When I was a student, I had to believe whatever my teacher has told. But now you can check it. You can go to IBM quantum computer, even with your mobile phone, And yesterday, Mitali must have demonstrated some such experiments, and maybe some others have also taken tutorial. So you just put a Hadamard gate. So Hadamard will make it 1 by root 2 0 plus 1 by root 2 1 when you start from 0. And then you do a measurement. You take a single shot measurement. It is either coming 0 or coming 1. You do it many times. Then more or less half of the time it's coming 0, half of the time it's coming 1. But in a real experiment, you see that you have not got the probability exactly half. I gradually increased from 1024 trial to 40946, 8192. But I did not reach it exactly 50%. So there are many errors in the systems, and 8192 is not a statistically large number. But if you go one by one, you will always see it is either at 0 or at 1 when you do one shot. So the fact that, which I'm claiming that it randomly collapses, you can check with a IBM quantum computer easily. I'll talk about another check later. So you don't need to believe. So once a random number is created, that's not sufficient for quantum cryptography. The random number must be distributed from one place to other place. So Alice and Bob must have the copies of the same random number. And so firstly, any key, whatever way you generate a key, has to be random. So distribution of a random number, different users will give you if you can do it in secure manner, then what you have in using quantum resources, then it will be called quantum key distribution. So that's the need. If you want a quantum internet or quantum network, it must be distributed among many users. But once you have a key, you must check the randomness of the key. Once you create a random number, so there are NIST tests. So this is a screenshot of such NIST test. So these modules you can download, but here is also an open problem. Say you buy a black box, like I bought something from ID Quantic. How do I know that something quantum is happening inside the box? Once the number is with me, it's a sequence of zeros and ones. So I can only check the frequency, that equal number of zeros are there or not. I can do many such tests, die-hard test and other tests, but I have no provision if it is in black box to check that whether the number is generated is actually quantum in nature. But I know something else. I know that only quantum mechanics can give you true random numbers. Classically, you cannot have a true random number, in the sense that if you're tossing a coin, if you know the pressure you are giving, you know the air drag, then you have to solve and you know the gravity, you have to couple of differential equations, Newton's equations, and you will be able to find out what is going to be the outcome. So that's not the case in quantum mechanics. It's collapsing randomly to one of the possibilities. So verification of this happens from another way. So this is called Mach-Zehnder interferometer. If a photon comes, and in the earlier experiment, when I have a detector here and a detector here, and half of the time this one was clicking, half of the time this one was clicking, it was not possible to check that quantum mechanics is really correct, or it's a ball kind of thing. Half of the ball is going here and half of the ball is going here. But if this experiment, these two are beam splitter and the other corner two are full mirror. So if 100 balls come, 50 ball goes up in the ball kind of model classically, then mirror reflect, and then out of 25 ball will go up, 25 ball will go to this detector in the lower detector. But if it is not like that, then what happens? If it is quantum mechanics is correct, you go to 0, you get a superposition of 1 by root 2 0 plus 1 by root 2 1, or reflected and transmitted. And then constructive interference happens in the top detector and destructive in the black detector. So the detector in the top always clicks, and that determines that the quantum mechanics is correct. Actually, collapse on measurement was happening, and it has a wave nature. It simultaneously exists to qubit exist. So do you need to believe me? No. You can use your mobile phone, use your Gmail ID, go to IBM Quantum Experience, and just put 2 Hadamard. So you start with the 0, put 2 Hadamard instead of 1 Hadamard shown here. So if you just put 2 Hadamard, that will be the output of the first beam splitter will go to the second beam splitter, and then you are doing measurement. So you will see that only whatever you will send, you send 0, you will get 0. If you send 1, you will get 1. So that you can do. Now, how this can help you to do quantum cryptography? So you are familiar with different kind of such interferometer. So the condition for interference is that you must start from a source, and Then unless it's laser, you create two sources out of that to maintain coherence. So here is a kind of interferometer that light goes from a beam splitter. Here is a mirror, it goes here, and the other part get. So they constructively or destructively interfere in different detectors. So we have already shown that if there was no absorber or bomb, then this detector D2 should have been clicked. So we introduce a new idea. Here is a bomb. So this is called Elizjar-Bedman bomb testing machine. So here is a source. If the bomb is here, then the light comes, and if the bomb absorbs the photon, it blasts. And if the bomb is inactive, light passes through as if it does not exist. And this detector clicks. So this is actually determining a wave particle duality experiment. So in wave particle duality experiment, particle nature is associated with the trajectory. So if light follows a particular trajectory, it's like particle. And when it is simultaneously present in more than one places, it's like wave. So when I put a detector here, the moment I detect that it is here, it means it is not here. And when this detector is not clicked, that means the photon is going from here. So I don't need to put two detectors. Absence in one path would mean that it is in the other path. So the moment I know trajectory, the wave nature is lost. Okay. So now the photons are coming. If the photon is going from this path, means the bomb is not clicked. So it has lost 100 photons I send. So 50 will go from here, and their wave nature is lost because I have put a detector here. So that's the particle nature. So 25 will go here and 25 will go here. So whenever this D1 clicks, that means that an absorber or bomb is present here. So without really sending any photon, I detect it. So that's called counterfactual. So counterfactual, that leads to quantum integration, counterfactual cryptography, etc. So now, in the last few years, there is a big debate between Zuberi and Vedman, and which is finally ended up. And we have a couple of protocols of counterfactual quantum cryptography, but I am showing you the simplest perception. So simplest one introduced from the picture A to picture C. So this is a Mach-Zehnder interferometer. Left-hand side is with Alice and the right-hand side is with Bob. And both of two absorber. So and that completely blocks. So if both of them, fourth thing is going to happen. Both of them have given this absorber. So no detector will click, no photon is passing. None of them have put this absorber. So D2 will click, as we have shown previously. If one of them has put, then in some cases, D1 will click. So whenever D1 will click, that implies that either Alice has put the absorber or Bob has put the absorber. Eve does not know who has put, but he knows that it is a successful case. But Alice knows whether she has put, Bob knows whether he has put. If Alice has put, they will consider it to be 0. Bob put, they will consider it to be 1. So now they will have a similar sequence of zeros and ones between Alice and Bob. Okay, so this is how interferometer can be used to introduce a kind of QKT. Now, this is a Mach-Zehnder interferometer, but this is an orthogonal state-based protocol. So Alice and Bob, so Alice sends Kate A plus Kate B by root 2 or Kate A minus Kate B by root 2. So these two states are orthogonal. Kate A plus Kate B may be considered to be 0 and Kate A minus Kate B may be considered to be 1. So now you see that there are two delays. So these are the optical delays. So the delay is such that when A goes from the upper path, Kate A, and Kate B, the packet goes from the lower path. So till Kate A is in the path, accessible to Eve, Kate B is not there. So but here is a delay in the A path. So A and Kate B reaches Bob's detector at the same time, but Eve is not getting access to Kate A and Kate B simultaneously. So apparently Alice and Bob can do measurement in the wave kind of basis, A plus B, A minus B basis, but Eve is restricted to AB basis. And in AB basis, the state will be probabilistic, give probabilistic outcome, but in A plus B, A minus B is a special basis. So this is called Goldenmark-Vedman protocol of orthogonal state-based cryptography. So this is another one, N09, and this is using Mach-Zehnder interferometer. So more or less things. Now, as I was telling that, classically, the whole thing depends on the complexity of a problem. So I explain it first. Suppose you think of a algorithm, classical algorithm, that how to add. So for addition, you write suppose you are adding 3 digits with 3 digits. So you first write the 3 digits, say 1, 2, 3, and then you are adding it to 4, 5, 6, and then below that you write 4, 5, 6, and then you add 3 plus 6 is equal to 9, 2 plus 5 is equal to 7, and so on. So you are doing it in 3 steps. So if you had n digits, then it would require n steps. So as the problem size is increasing, the number of steps is increasing. But how fast? It is increasing in this addition case linearly. Now you think of multiplication. You write the same 3 digits, 1, 2, 3, and 4, 5, 6. Now you have to multiply 3 digits of the first number 1, 2, 3 with 6, and write and then below that you have to write 1, 2, 3 multiplied by 5. Then you have to write 1, 2, 3 multiplied by 4, and then addition. So this requires more steps. So a problem which requires more steps are more complex. But if the number of steps goes like proportional to n, log n, or n square, n cube, then we can do, or any polynomial of n, then we can do it in reasonable time. So it does not go very fast. And those are called, all those problems are under same complexity class or same difficulty class called P. But if I don't know any algorithm which can solve certain problem in polynomial number of time, then it is called that it is not reducible to polynomial or NP. So NP is a class of problems. Such problems cannot be solved fast, but if a solution is given, it can be checked easily. So suppose I take 2 large prime numbers, multiply that, and give you the product. And then someone give you a solution and ask you to check the solution, you will be able to check it easily. But if I ask you to do factorization, then you have to divide this number. Suppose P is a prime and Q is a prime, and the product is PQ is equal to capital N. So to factorize capital N, you have to divide it by 3, 5, 7, 11, up to root over n, all the prime numbers. This is a crude method. You can check something little better, but you will require a large number of steps, and prime factorizations cannot be done in polynomial time. So classically, this kind of problems, this kind of one-way problems whose solution can be checked easily, but who cannot be solved easily, are the backbone of the classical cryptography. So RSA cryptography uses this factorization problem, Diffie-Hellman uses discrete logarithm problem. And the bigger is the problem, the longer time will be required to break it. So for example, what should be the bit length? So normally you use 128 bit or 256 bit, but if you use 2048 bit, it may be secure up to 2040 or, so the larger the key size, the communication is more demanding, but this will be secure for longer time. So that's the notion of classical security. Here, you are assuming that your if or opponent does not have a machine which is more powerful than what you have estimated. He does not know a polynomial algorithm to solve the same problem. Because in no problem, you can see proof that there should not be any polynomial algorithm. So someone can have a better algorithm, just like Hitler's code was broken, and then he can break it. So this is conditional, whereas quantum mechanics gives you unconditional security. Now, to understand this notion of complexity and the problem, I just tell you something more. So the Grover's algorithm, somebody may have taught already in this summer school. So Grover algorithm is something for unsorted database search. And if you have telephone directory, one side is the name, it is ordered according to name, but not according to number. And someone asks you to search it. And sometime you may do it in crude method by one search, sometime it may take n search. So on an average, you need n by 2, which is of the order of n. But Grover can do it in root n. So if you use quantum resources. So interestingly, this can be used to attack many of the cryptographic protocol, including so-called post-quantum cryptographic protocol, but root n is not a big saving. So just by increasing the size, you can get rid of root n type of attack. But here is a teacher, he asked a student that if I give you a phone number and ask you to find out what is the name of the owner of the phone, how many searches you need? So a student tells that he can do it in one search. So he will call that person and ask his name. So he may or may not accept the call. So this is not a protocol. This is not the way we consider complexity. But you understand that there may be a situation when the man really picks the phone and tells his number. So then you beat the complexity, which was expected to happen in 1 million times, you can do it in one time. So that always there is such a problem in conditional security. So you consider that somebody has to factorize n is equal to p by q, and he accidentally, whatever minimum be the chance, he accidentally randomly choose a prime number p and divides and it matches. So always in conditional security, that kind of things, probability is very less, but that will be there. Then the other point, in this cartoon, we share that a student got F grade and the teacher is telling that you have not solved any problem, and the student is answering, well, with respect to all the algorithms I knew, these were in NP. So, and since it was in NP, I could not solve it in the 3 hours of exam. So the teacher is telling that if you don't study, everything will appear in NP. So whether a problem is in NP or not, that do depends on our knowledge. Tomorrow there may be an algorithm, there may be a clever algorithm which I don't know, and I'm thinking it to be in NP. So for example, prime factorizations can be done in polynomial time if I have a quantum computer. And that's what is done in source algorithm. So source algorithm or source paper solve both prime factorization and discrete logarithm, and consequently RSA and Diffie-Hellman become vulnerable. But still people are using. The market for quantum cryptography is not that big because the large quantum computers has not yet been built. But the things are changing. So things are changing, and here we list that gradually the quantum computer is becoming big. Like IBM has claimed that they have a 49-qubit quantum computer. Some people have 52-bit quantum computer. Google has already claimed the quantum advantage experiment. So with respect to that, quantum computer size is increasing, and the resource required for doing factorization is reducing. So in source original algorithm, register size is very big, but now people are using hybrid quantum thing. So we tried, but we can factorize only 35. But there are other reports like D-Wave processor factorized 2,99,000. Lee et al. Factorized about 3 lakh, a large number. And Professor Panigrahi, who is organizer of this meeting, has factorized using IBM quantum resources a number which is little more than 90 lakhs. So the whole point is, gradually the point is approaching where RSA is more and more in danger. Now, this part is keeping the students in mind that how really quantum cryptography is done. So this is a kit which can be there in the experiment lab. We have just recently bought it. So this is a third lab kit. Here is a laser, and here is the laser always gives you a horizontally polarized photon. So you just put a polarizer in front of that and show that. Here is a polarization rotator, which you can rotate and decides that the outcome will be horizontally polarized, vertically polarized, 45 degree, 135 degree. So this is something which you are doing by hand, but in reality, you can do it automated. So a random sequence of 0, 1, plus, minus, or horizontal, vertical, 45 degree, 135 degree photon comes. Forget about the middle block now. So here is a Bob. So Bob can also has the similar polarizer. So if Bob places it in horizontal direction, then the horizontal light will pass. But if I were coming a horizontal polarized light and he puts it in 45 degree, so he also has 4 choices and he is giving it randomly. So if you put it in 45 degree, then horizontal polarized will appear as plus, minus, ket plus, ket minus by root 2. So half of the time it will be ket plus, half of the time it will be ket minus. Here is something called polarizing beam splitter. So polarizing beam splitter allows the horizontal light to pass and vertical light always gets reflected. And here we have 2 detectors. So looking at the detector, I will know that whether it's a plus state or a minus state, or depending upon this polarization, and we'll have a sequence of 0, 1, plus, minus, etc. So the whole thing is like this. There is a light source. There is a random polarization between 0, 45 degree, 90. Forget about Eve. Bob is also doing the similar thing, 0, 45, 90. So the question is whether the Bob's basis matches with Alice's basis or not. So all those cases where Bob basis matches, they should get the same result, and we'll keep them in the next sequence. And all those cases where it does not match, we'll drop them. So all the cases where it match, I will compare whether I'm getting half of them. I'll compare to check that whether eavesdropping is happening or not. So this setup does intercept recent data. So it's in the lab. So what it does, here is Eve has you see that Eve has a Bob kind of setup where he is doing measurement, and whatever outcome he is getting, then he has a Alice kind of setup. He is repeating it and sending it to Bob. But if I send a 45 degree, say I use a plus minus basis, 45 degree, 135 degree, and this guy, Eve chooses a wrong basis. Polarization rotated in 0 degree, 45 degree. So Eve chooses it Eve measures in 0, 1 basis. So I send a plus state and Eve measured it as 0 state. So Eve sent back a 0 state, but Bob will keep only those cases when he is using plus minus basis. So he is supposed to get a plus state as plus state, but 0 with half of the time will go to minus. So in those cases, it will be detected that there is an Eve. So half of the cases, Eve will choose a wrong basis, and half of those cases will be detected. So 1/4 of the time, Eve will be detected. So that makes difference between classical cryptography and quantum cryptography. Classically, I don't have any means to check that some eavesdropper is there or not. And cloning is also allowed. Here, copying quantum information is not allowed. So Alice cannot make a copy and wait for later time to do a measurement. So that leads to BB84 protocol, and I'm not repeating. So Alice chooses randomly his basis, Bob chooses randomly his basis, and only those cases. So here you see the diagonal basis and plus basis. So this is I'm not taking. So next step, I'm taking all those cases where the plus, plus, cross, cross, plus, plus. So basis matches. Half of them I need to compare that Eve is there or not. If Eve is not there, so we take this kind of data and then compare. So how this is connected to modern experiment. So this is what happens, that you are sending this 0, 1, plus minus kind of states, and you are keeping all those things where the basis matches, and from that you have a shifted key, and then there are many steps and you get the final result. So here is a port for satellite communication. One is in Calcutta and one is Delhi, say. So first the key is established between Delhi and the satellite, then a key is established between Kolkata and satellite, and then he discloses XOR operation of these two keys, key 1 XOR key 2. And since the station 2 knows the key 2, he does another XOR operations, and key 2 cancels, and he left with key 1. So now both parties have key 1, satellite's role is over, and using that key, the video conference happens. So this is what the satellite cryptography works. So it is not only the Chinese team. So there are many satellites, and most of them are in low Earth orbit. And if Urvashi speaks in one of the sessions, means she will probably speak in more detail, or RP will speak in more detail. So whole point is now, the title of the talk was expectation, challenges, etc. So what is the expectation? Expectation is that someday the situation will be like that. Everybody is closing the bank account in the classical bank, which has experience of 50 years, and everybody is opening account in the quantum bank, which will give quantum security. So this girl is asking what happened, and this man is answering that yesterday a quantum computer has been developed or launched. So this will not going to happen all on a sudden. It will be a gradual improvement. Reason being, there is a challenge because of decoherence. So whatever qubit I make, so as I was telling that it is the qubits, as you measure it collapses. So it can be unintentional measurement also. It can interact with the environment and collapse itself. So everything apart from the system is environment. So in this slide, a candidate came for an interview in quantum computing, and people asked that, what is your credential? Have you done anything on quantum computing? He told that I was part of environment in every experiment. So environment is the villain. So that leads to noise. And because of noise, we cannot make big quantum computer. We cannot tolerate fault. Gradually, we are improving, but it's still a long journey. And since the large quantum computer is not built, so far, the really RSA or Diffie-Hellman is not broken in the realistic world. So the market of quantum cryptography is not very high, although quantum cryptography products are already in the commercial market. Finally, where from the security come? So here is a girl, and plus fish is mermaid. So the teacher asked, give an example of quantum superposition, and the student told mermaid. So But then the teacher tells that, well, nobody has ever seen marmoset. And the student tells that if you do a measurement, it collapses either to a fish or to a gull. So teacher told that, well, that's not the case. So in quantum world, you can do a measurement in marmoset basis also, in a basis where marmoset itself is the element. So where from the security comes? Security comes from, by hook and crook, I make the marmoset basis unavailable to Eve. So in BB84 protocol, it was the general inability because non-orthogonal states were used. It's our general inability that I cannot simultaneously do measurement with arbitrary accuracy in two mutually unbiased bases. But in Goldenberg-Hedman protocol or POP-based protocols, these are orthogonal state-based protocols. So in POP, the information about which particle is entangled to which one is not available. In GB protocol, Kate was available in a time when Kate B is not available. So by some means, I have to make this marmoset unavailable or the spatial basis unavailable to Eve, then I have security. So that was the basic. With keeping this basic, there is a structure. So I'll be happy if you understand up to this point. And so it's more or less time, but for next 10, 12 minutes, I'll give a faster exposure to things of the general structure and such things. Means I'll be fast I was very slow up to this point. For next 10, 12 minutes, I'll be very fast before I finish. So there is a general structure which is shown in this slide for cryptographic protocol. But quantum cryptographies, one has to understand that all the discussion about QKD, but QKD is just a layer. So QKD itself is not application. You just have a key. Key is random. So you generate a random number and somehow you distribute it. That's not everything. Well, to start a QKD, you must do authentication that Bob is really talking with Alice or Alice is really talking with Bob. So authentication is a big part. For authentication, some kind of OTP, like you have your PIN, should be there, which must be pre-shared. So everything is not really happen as public key cryptography. This is previously shared. This part is not always quantum mechanical. So a completely quantum mechanical private public key cryptography is impossible. So something you have pre-shared, whatever small it is. Then you generate a key and part of the key you keep for next round. That next round you will use that 10% of the key for authentication. Next round you make a key. So in that sense, QKD is actually key amplification because already a key was kept there for authentication. But QKD, top of QKD, we first do error correction, privacy amplification, and on top of that, there is the secure communication, which may be classical or may not be classical. And I skipped something for first, but in the security proof, we now discuss something in the Renner way that there is a realistic situation and there is an ideal situation. So it is easy to show that something is secure in ideal situation, but their difference is epsilon. And so we define different kind of thing that a QKD protocol is P-real, protocol P-real is epsilon secure if it is epsilon indistinguishable from an ideal protocol, P-ideal, which is perfectly secure. That is, ideal protocol can be proved secure, but then we find out the difference with the real things. And if the epsilon is very small, then we call it epsilon secure. A QKD protocol is epsilon correct, epsilon secret, or epsilon robust is defined in this way. And that's the modern language of talking about security. But it's not, as I mentioned, it's not restricted to, only about communication, voting, etc. are also important. And in 2007, ID Quantic was successful in selling a quantum cryptographic solution for internet voting. But this paper put many questions on security aspects of quantum cryptography. Initially, people used to think that quantum cryptography is unconditionally secure and it can solve every cryptographic problem. But then we found that it does not work for many cryptographic problems. For example, bit commitment, quantum oblivious transform. So these things cannot happen in two-party scenario. For quantum remote coin tossing, in two-party scenario, security of this cannot be proved. So Low Chow make it possible and extended this idea to computation. So how security appears in computation? Suppose you have a function f of ij which has to be calculated. And this function is such that it is equal to 1 if I is equal to j. And is equal to 0 if I is not equal to j. So that means it can compare I and j. But if a person who is computing this does not know the value of I and j and cannot conclude anything other than whether I is equal to j or not, so that's a secure private computation. So this problem has a name. It's called socialist millionaire problem. So two socialist millionaires wanted to compare their assets, but they don't want to disclose how much money who has. So there are many versions of this. These are called post-Cold War problem. Suppose Russia and America at that time wanted to dispose of some nuclear weapons, but nobody want to disclose how much they will. So they want to come on the same number, but nobody want to disclose it beforehand. So they can compare in this way. And so this is called socialist millionaire problem, quantum private computations. So this is easy. So Barn give a protocol of quantum dialogue. So it works in this way. Alice starts with a Bell state 0, 1 plus 1, 0 by root 2 or 0, 0 plus 1, 1 by root 2. Keep one photon with himself and herself and encode Pauli operation I, X or I, Y or Z. So I is identity, X is not get, and to encode 0, 0, 0, 1, 1, 0 and 1, 1 and send the qubit to Bob. Bob does the same operations and send it back to Alice. And Alice does a Bell measurement, and if she finds that the initial state and final state is same, then she knows that the product of her operation and Bob's operation is identity, and identity can happen in 4 ways. So I times I, X times X, IY times IY, Z times Z. So similarly, if she got that the product of their operation is X, then they know that either Alice has applied I, Bob has applied X, or Bob has applied X, Alice has applied I, or one of them has applied IY and the other one has applied Z. So there are 4 possibilities. But since Alice knows what she has applied, she knows what Bob has applied. So what is Bob's encoding is known to her now. So Eve also knows, and then it doesn't. He announces the measurement outcome. Since Bob knows that what was he applied, so he knows what Alice has applied. So they will know each other's state. So quantum dialogue is very interesting. If you can do quantum dialogue, if only one party does the encoding and other party does nothing, then it will become quantum secure direct communication. If instead of sending a message, you send a random key, you have a random number and you send that output, then quantum key distribution will happen. So many things can happen about its subclasses. But there is a problem. The problem with the Barn algorithm is that both of them are sending 2 qubit each, but Eve's ignorance is only of 2 qubits. So there are 4 qubit transmission, but Eve's ignorance is 2 qubit only because Eve has to choose between 4 operations. So log 2 base 4 is 2 qubit. Now, how can this be used for computation? So now I introduce a Charlie, and Charlie starts with this state and sends 1 qubit to Alice. Alice encodes, send it to Bob. Bob encodes and send it to Charlie. Charlie does a measurement, and if it is the same state, then the encoding is same. If it is not the same state, then the encoding is not the same. So quantum private comparison is done. So we'll not repeat this. Now, here is a voting protocol. So voting is a computational task. So there is similarly for auction protocol. So auction, voting, etc., online shopping are such tasks which are used in daily life. And if I can do using them in quantum resources, especially auction and quantum auction, seal bid auction can reduce corruption, and quantum voting can increase the authenticity of the voting and strengthen the democracy. So democratic structures can be affected by quantum technologies, and notion of security of voting, auction, etc., will be changed with the more realistic application of this thing. So here is a QD kind of states, Hillary's protocol, and it's an entangled state. It's like 0, 0 plus 1, 1 plus 2, 2 plus 3, 3 plus, and so on. And if there is somebody votes a yes vote, then state K means so 1 qubit is kept with the controller and the other qubit moves through the channel. So first voter, if vote yes, it gives K plus 1. Second voter vote yes, it becomes K plus 2. Third voter does nothing. So he votes for no and so on. And finally, when a measurement is done, then it will be K plus LK state. And then L number of people have voted yes. If that's greater than N by 2, then you know that who is winning. So I already mentioned that with the advent of IBM and AWS and cloud-based computing, it's now required that delegated quantum computing happens in a secure manner. So people have already started this kind of thing. So if you have a classical computer which can generate single qubit, then you can send it to a Bob who has a quantum computer, and you have a classical channel, and this delegated blind computing is allowed. If you can do a measurement, quantum measurement, then also delegated blind computing is allowed. But if none of this is allowed, you only have a classical computer and the classical channel to talk with quantum computer, then delegated blind computing is not possible. So that implies that if cloud-based services has to happen and we have to take it in a secure manner, then the next generation of the classical computer must be added with some quantum resources. But can we extend the ideas for a classical user? Because most of the users will be classical. The answer is yes. So here is a simple protocol. So here a classical user can do a measurement only in computational basis or just reflect the state. And when he does a complex computational basis measurement, he can reproduce it in 0-1 basis and send it back. So as like in BB84 protocol, Alice prepares 0-1 plus minus and the random sequence is sent to Bob. Bob either measure it or reflect it. So 4 kind of things is happening. Alice prepared in Z basis, Bob measures. Alice prepared in Z basis, Bob reflect. So on the reflected cases, Alice must have the same result, whatever she has prepared. So in the basis she prepared, she does a measurement. And if it matches, that means Eve is not there. So that's just like BB84. And if Eve is not there, then all the cases where Alice prepared in 0-1 basis and Bob measured in 0-1 basis, the result should match, and that should lead to a key. So the key generation rate will be smaller, but key is possible. So I skip the semi-quantum e-commerce, etc. And now I tell you that although this is exciting that it can give unconditional security, but there are various ways to attack it. So it is a simple one. So I have to create a random sequence of 0-1 and plus minus. So some horizontal, vertical, diagonal basis. So I put those polarizer. So this is a vertical polarizer, this is a horizontal polarizer, this is a anti-diagonal, this is diagonal, and the lights are coming through beam splitter, they're mixing, and then it's going here. But now Eve sends a vertically polarized strong light through a circulator. Circulator is a device. If it comes from port 1, it goes to port 2. If it comes from port 2, it goes to port 3. If it comes from port 3, it goes to port 1. So the light comes here and enters. And when it reaches vertical polarizer with certain probability, 100% of the light passes through and it changes its temperature, and so the wavelength is changed. It cannot go to horizontal polarizer. So horizontal polarizer wavelength remains same, lambda 1, and it's horizontal polarizer. In the other 2 cases, because of Malus law, 50% of the light goes to diagonal and anti-diagonal through the diagonal and anti-diagonal polarizer. So temperature change, but not so much. So its wavelength become lambda 2. So now measuring wavelength, I can identify this. So although I cannot do measurement on simultaneously in HDA basis, but I can do a measurement in wavelength and attack this. So how to remove it? So Alice should put another circulator, so light will not come in Alice's port. So if anything comes, then that will be thrown away. But this was an attack. So many such attack happens, and attacks are divided into 3 classes: coherent attack, collective attack, and individual attack. So most of the attacks which you can do at the moment is individual attack. So I don't have much time. So I skip this, but I just tell you that although you can do only individual attack in the lab, but your protocol must be proved against the coherent attack. Now there are many things associated with wavelength. So your beam splitter, you are taking a 50-50 beam splitter. So most of the BB84 kind of implementation, I start with a 50-50 beam splitter. And so part of the light goes in port 1, part of the light comes in port 2, and say half of the light. And then I put a polarizing beam splitter here. So the polarizing beam splitter allows the horizontal light to pass and vertical light to reflect. And then I put detector. So this does a measurement in horizontal vertical polarization. So randomly measures in 0-1 basis. Here I put a wave plate. So wave plate changes the angle of incident light by 45 degree, and say 45 degree polarized light become 90 degree and 135 degree polarized light become 0 degree. And then it passes through a PBS. So it, and then horizontal and vertical is measured. So this wave plate followed by horizontal vertical PBS followed by 2 detectors does the measurement in plus minus basis. So random measurement in 0-1 and plus minus basis would means that randomly the light will go to port 1 and randomly the light will go to port 2. So ideally your system works in this way. But if you can change the wavelength of the incident light, then the beam splitter, which is 50-50 beam splitter in certain wavelength, is not 50-50 beam splitter in all wavelength. So you see how it varies. So in 1450 nanometer, this is 1. 1 means I port 1 by I port 2. That means all the light is going in I port 1. And here it is 0. So I ideally do in the teleportation range in 1550, but if I go in 1440, 50, it will go in 01, it will go in the port 1. That means all the measurement will happen in 01 basis. And if I make it 1650, all the measurement will happen in plus minus basis. By changing wavelength, thus Eve can attack. Eve will already know that in which basis it will be measured. So there will not be any ignorance. He will already know the outcome. Now, the detector mismatch attack. So when you buy detectors, then there are efficiency like this. And at a particular time, both of them are efficient. But if you change the arrival time, then in this time, you can see that eta 1 is more efficient. So the first detector will click. And this time, the 0 detector is more efficient. So if you, by controlling this, you can decide that which detector will click. So there are many detector blinding attacks which we are not discussing. So here is something called Trojan horse attack. So Trojan horse attack is very relevant in other kind of, continuous variable cryptography as well. So here is a laser. So part of it goes like the reference beam from the beam splitter. Rest is modulated, reflected, and reaches here a circulator. So anything comes from here, goes here and reaches Alice's port. So it gets partly reflected from Alice's different devices, controller, VAC, etc. Say commutator, variable attenuator, connector, variable attenuator, detector, phase modulator, and everything giving a peak. And here some kind of phase information comes, and looking at this, so when the light will return, then it will go from the second path, because anything coming from 2 will go to 3. And comparing with the reference beam, I will know that what phase changes happen, and I'll be able to get some information about what is happening inside Alice's port. So this is called Trojan horse attack. So to stop it, Alice also has to use a circulator. So finally, here is a discussion between a boy and a girl. So the boy told that I don't trust you. The girl says that why? And the boy said that because you reflect light. So the girl said that that's why you can see. So then the boy said, but Eve can also see. So to avoid that Eve can see what is happening inside Alice's port, Bob must buy a circulator to Eve and Alice. That's why Alice told that, then gift me a circulator. So this is a glimpse that what is Trojan horse attack. So the takeaway message is that security is not only restricted to quantum cryptography, it's beyond that. Quantum computation can happen, and success in developing large quantum computer will have an influence on the market of quantum cryptography. It's unconditionally secure. We understand what is the difference between conditional and unconditionally secure, but it requires real physical devices, and they can be exploited to attack. So we discussed some attack. And we mentioned that if you see the security in the broader perspective, then there are situations like military applications like quantum radar. There are situations like detecting a submarine where also security things will influence. So quantum metrology. So every aspects of quantum information has something to do with the security, and the notion of security will be completely changed in a quantum world, which is expected to arrive in maybe in few decades. Gradually, quantum cryptography solutions are already in the market, but other things has to improve too. Each depends on other. Means the market will be larger, the product will be in daily use only when the other things happens. So I'll stop here and I'll take your questions.
Thank you, Anirban. Can you see the chat box? There might be some questions in the chat box. What happened was mine was restarted, so I have lost the questions.
Let me check.
My computer restarted somehow. So you can come out of the presentation mode.
Okay.
Yeah, now you check the chat box. There are no questions, huh?
No, there is no question. It's
okay. So let us open it for discussion. First, people who are logged in, they can ask directly. Prashant, is somebody monitoring the YouTube live link to see if there are?
Yeah, Avinash is there. But let us start.
Okay.
Generally, students say, Anirban, You have
Yes.
been involved in writing the roadmap, for in this quantum communication and quantum computation in India. Maybe can you, since a lot of young people are there, can you just add a few lines here about that?
Sure. So this is more about opportunities. So
yes.
There is already we have a mission called Quest, Quantum Enhanced Science and Technology, and that's a DST mission. And many of us have projects. Means most of the speakers will have some projects in that. And Quest advertisements are there. And if you are already MSc, you can have look for JRF. If you are PhD, you can. So even we have some proposal. But this was a smaller thing. Then a new thing come called National Mission on Quantum Technology and Application. It's a NMQT in short, and that's a 8,000 crore project. So this is already mentioned and implemented in budget, but then we have been asked to write a proposal. So this has 4 legs. So one leg is on quantum metrology, one leg is on quantum material, one is for quantum communication, and one is for quantum computation. And this will be a huge thing because this will also keep options for ITI people to develop technologies, polytechnic people, engineers. Means it will not be restricted to MSc physics people or MSc mathematics people. So we require a lot of engineers. Means many people from different background will have options, and there will be options for developing companies, means startups, and it's expected that and there will be a big structure, and then there will be sub-components, and once it is approved, the clarity will come that how it evolve. But there will be options for engineers and mathematicians, physicists, electronics people, everybody to contribute in it, and it will come in a big scale. And there will be many jobs, and the jobs will go beyond academia because there will be industries, and there will be a special focus on developing industry as well. So NMQT means especially those who were doing PhD, they can get benefit after 1 year, and who are just now in MSc first year, they maybe already get this NMQT thing in next year. So it is in cabinet, means once the cabinet approval comes, then it will start.
So another thing I wanted to ask you, since you are working on this cryptography and bidirectional communication, are there any technology out of that bidirectional communication?
No. These experiments, what means most of the experiments are done by Long in China. So there are some other experiments also, but there is a gap between these experiments and the theory. So in theoretical paper, it is assumed that there is a quantum memory. And in place of memory, what they are using is quantum delay. So they are delaying it for a fixed time. But delay is not quantum memory. Means so these experiments are essentially proof of principle experiment. They are not. There is a difference. Means so unless a good quantum memory comes, this will not be a good type of experiment. Means it's all proof of principle experiment.
So see, for example, why there is a fundamental problem with memory? People always point out that why is it difficult?
No, it's not fundamental, but it's a challenge. It's a it's more like technological thing. I mean, quantum mechanics does not stop you to have a memory, but the technology is not there.
I remember, in coal atoms and other materials, they used to store for seconds. This group in MIT.
But some kind of transmission, transducer should also be required, because I am working in optics. Means that it has to be read from optical qubit and then successfully convert into atomic qubit and then return back to optical information. So the challenges, these are more technological challenges, and that's why engineers have to do certain things. Means they do have some problems to contribute.
Okay, so thank you from my side.
So about that Thor Labs equipment that you showed, how much is it? How much does it cost?
Oh, this is like a MSc kind of experiment. This is 3.5 lakh. So we bought another Thor Lab thing, the bomb testing kit, and if we combine these two, then we can do several experiments of MSc level. Means this is they claim that it can be used for doing BB84 protocol.
Okay.
But we have implemented B92. We have implemented SARG04.
Okay, very good.
And then since there are two, and we're taking some optics from the other experiment. So we have implemented this Talmor's protocol of semi-quantum cryptography also.
Oh, okay.
But all these are engagements.
Yeah.
What happened? Experiment like
what happened to your grant thing purchase?
No, nothing. No progress. Means institute is more or less closed. Means no progress.
By the way, we have started setting it up. So in 1 month's time, we will start having some data on ODMR.
So for playing means buying these things means for a lab like ID Quantics random number generator.
Yeah, how much is
this
it?
kind of
how much is it?
So if you can buy directly, it is $1,000. But when you buy through this ID Quantics dealer, then after tax, it's costing something like 1,40,000.
Okay, so that includes custom duty also, no?
Customs duty, freight,
and GST, etc.
But we are using this random number generator and generating sequence in the lab, and then the students are using those to decide that in third lab that polarizer will be in 45 degree or 145 degree. So you use a quantum random number to choose the random basis.
There's something like what you were showing in the talk. Yeah.
But this is thing that it's not automated. Everything is happening by hand.
Something similar was shown by Professor Thagarajan also in the morning. Exactly this thing, like the random generator, and then you rotate the polarizer by hand.
So this we have done in the lab, but it's more like a toy. I mean, this is not for research,
I understand, but it's good to motivate.
It's very good for MTech students or that kind of project, and especially it can go beyond. If you have some optics in the lab, then it can go beyond what they claim. So they claim that they can do BB84. We can do many protocols.
Right.
And so, Anirban, because you are sitting in Delhi, see, there was this initiative from MIT that they will, in a bucket kind of thing, get these things and we can apply for grant and use. What is the status now?
No idea. Means I have not spoken recently. Means I don't know.
Delhi was under lockdown, but now it is. Okay, so well, thanks Anirban very much. So now is Devashish's talk. So
Thank you.
Let's thank everyone. Everyone. Vedant, we have 2 minutes. Devashi has not come yet, no?
No, I am.
Devashi is there. Okay. You can. Okay. Can't see your face. Okay.
No. Only head is visible.
Head can be seen. Can you lower the camera? Right.
So how are you now, Devashis?
Yeah.
I am now okay, but weakness remains. Actually, when I outside my house for some work 2 days ago, I find that weakness remains. I am not totally fit till now. But otherwise, in the room, I have no problem at all.
See, one of our colleagues also, you might be knowing, Anirban knows. Ayan had a very severe case of corona. We had to admit him in ICU. So he has still not completely recovered. He's weak. So if he climbs stairs, then he is out of breath, like that kind of thing. So,
actually, second strain of COVID. This COVID is very dangerous.
Yes.
Not like the first time. So many people throughout
they're saying,
India.
yeah, now they're saying a third might come. So that will be
Yeah.
yes.
And that's
If not, it is already there.
Yes. Already there are some patients with third.
Devashish, otherwise parameters are okay.
Okay.
These blood related parameters.
Blood related parameters are in control. I have tested 2 times. So with a cardiologist, I have a very good cardiologist. I have always in touch with him. And he had tested 2 times my blood. So it's now okay. My D-dimer is very high when I leave the hospital.
Okay. Now it is normal.
Now it is under control.
Which hospital were you in?
Oh, that is actually nearby all the big hospitals. There is no seat. I don't know. Actually, I am almost out of my. And then at Behala Apex Hospital.
Behala Apex Hospital.
Behala.
No, it was very bad. My own PC passed away. We could not get a bed at all for that. So.
At that time, when I am infected with COVID, that time very serious in Calcutta. No bed is in everywhere.
Okay, so let us get started. So let me introduce you. So welcome everybody. For this session, we have Professor Devashish Sarkar from Calcutta University today speaking. So Professor Sarkar is actually a mathematician, an applied mathematician, and he is also in the Department of Applied Mathematics in Calcutta University. And he did his PhD also from Calcutta University. And Professor Sarkar is one of those people along with Professor Guru Prasad Kaur and other Shivashish who are from applied mathematics background and who has been contributing heavily. So his area is quantum foundation, quantum information and computation, fuzzy topology. So these are some of his areas. And he has actually graduated a lot of students who are very well placed in different parts, and he also collaborates extensively with other people. So without further ado, I would hand over to Professor Sarkar, and his title is Local Distinguishability and Indistinguishability in Quantum States, a brief introduction. So Professor Sarkar, 1 hour talk and 15 minutes. 1 hour talk and 15 minutes.
Thank you, Chiranjeev.
Yeah. So you can start presenting.
Also Prashant.
Yeah. You can start presenting.
Is it visible now?
Yes.
So thanks a lot. Last year, in 2019, I also be at ISER Kolkata giving possibly 1 or 2 lectures. So this year also I am giving, but the subtopic is somewhat different. This year I am choosing this subject because this is very one of the most important part of quantum information theory. This local distinguishability and indistinguishability of quantum states. Many people throughout the world are doing research in this field, and in our country there are lots of people, young people also doing very good research recent days. One of them is Manik Saronath, and my collaborator earlier, Somsubro, also doing very good research in this field. So we have also some papers in this field. Now I am choosing this field because it is not only interesting, it will give you the basic flavor of quantum information theory, by which you can interested to be looking about the quantum information entanglement and other things. So my recent collaborator is my scholar Otunu and my colleague Indrani. So I am starting my lecture. Now, what is the basic tasks in this lecture I will cover? First, the basic task is to distinguish a class of states in a composite quantum system by LHC. Suppose you have given a set of states, and a state is shared between 2 or 3 or more parties. Now, all of you have to identify which state you are shared from that state, and you only allowed to do LOCC, means local quantum operations, along with classical communications. So this is the restriction you have, that the operation should be local one. You can use classical communications, by which you have to judge whether what state you are actually getting from the set of states. This is the basic problem in this subject. Next, since only LOCs are available, but for distinguishability, we require orthogonality, perfect distinguishability. Here we will talk about the perfect distinguishability, that is with probability 1. So the all states of the set are orthogonal to each other. So it is given. So globally they are orthogonal, but locally you have to identify. Therefore, all are distinguishable globally. So if all the parties are in a lab, they can do the global operation and they know that what state they are sharing. But if all are in distant labs, so then you have only operation you can choose, it's a local operation. So the problem is somehow on this fact that if all the labs are situated in different parts of the world and other place, then what to do? How do we know that which state we are actually sharing? This is the basic thing. Now, another thing I have assumed here, that number of states here we will take the finite, not infinite case we are dealing with. Okay. Now, what are our considerations in this lecture? Firstly, we will give you some results on pure bipartite system. There are many results which give you the basic flavor of this subject. Mainly single copy case. That means you will take only one copy of the state from a set, not the 2 or 3 copies. And obviously, this distinguishability question with certainty means with probability 1, you are able to distinguish the state you want given to you. Now, to give much better flavor, I will explain the case of Bell states and generalized Bell states. I will explain what is meant by generalized Bell states. Bell states may be familiar to all, but may not be generalized Bell states are familiar to all of you. Everyone know Bell state, but general Bell state are not much known. But some people also know that what is generalized Bell state. Next, after that, I will discuss about some class of, this is a class of mixed state, very interesting. Smolin gives first the definition of this kind of states. This is called a class of activable bound entangled states. Indrani with Bhavani and Somsukra will generate this class. Simultaneously, Hodaki group also provided this same type of class of entangled states. Okay. So lastly, we will provide our group's recent work on tripartite product states and discuss indistinguishability of those class of tripartite states. So I will add lastly some of recent work in this lecture also. So before going to the main things, I am just pointing out what do you mean by quantum physical operations, because all these operations needed to do things is a physical operations. So otherwise you cannot do the proper experiments or something else. So these things I am just mentioning. Suppose a quantum system is described by a state rho. Now by a physical operation on rho, we mean a completely positive map acting on the system, and it is described by Krauss. From Krauss actually give the basic mathematical form. You can write it is at epsilon rho. This is the transferred state. and it could be written in the summation form k from finite or infinite. This sum depends upon the system you are choosing. So it is AK row, AK dagger. There are some problems. People are trying to find the how many minimum number of AKs needed to describe a physical operation. In coherence theory, that is very important. So this sum usually varies from many numbers. So, but there are some questions. What is the minimal number of k for a particular type of operation? Okay. Now, these AKs are nothing but the linear operator that satisfies the relation that sum over k, AK dagger AK is less than equal to I. When AK dagger AK is equal to I, then it means that this is something trace preserving completely positive map. Sometimes it is written as CPT map, and otherwise only it is not transparent. It is simply a CP map. You can remember that by physical operation we mean a kind of operation which transfers a state to a state. That state may be on the different Hilbert spaces, but it always transfers a state to a state. Otherwise, it would not be okay. And by this, these properties are generated by people around the world. Benjamin Schumacher and other people have described these things, and Krauss has given the basic formalism. Now, a particular type of physical operation is very much useful in quantum theory. Information theory, these are called separable pattern, and on which this LOCC are the what kind of physical operation you can call separable superoperator. Suppose a quantum state is shared between a number of parties, say A, B, C, D, etc. The many numbers. So it is basically you can think bipartite, tripartite, or multipartite system. And each AK that what I said in earlier slide could be written as the tensor product of the operators on the particular system Hilbert spaces. Suppose it is written an LK, LKB, LKC, ABCD means the particular system operator, LK, BC, and these are different linear operators on the separate individual Hilbert spaces. Then and the map usually is called separable superoperator. So this map actually separated out in the different individual Hilbert spaces. So it is named as separable superoperator. Superoperator is point in the time because rho is a density operator. So this superoperator or the physical maps, they are acting on the operator. So this superoperator term comes out. Okay. Now, by what is LOCC? By LOCC, we mean a physical operation where each party can perform quantum operations in their subsystem. So for LOCC, we need at least bipartite system. So it is generally basically a multipartite system. So we mean a physical operation where each party can perform quantum operations in their subsystems and communicate their results to others. So each party could do many rounds of quantum operations, but for each round, they have to communicate the results to other parties. And both, all the parties will do the same thing. And this project could be performed in principle infinitely many rounds. If it is done by some finite round, then it is called finite LOCC. And if it is done infinitely, in principle, then it is called infinite LOCC. Okay. So there is a very important question for a long time that whether separable superoperators could be approximated by LOCC or not. So, or you can written down a separable superoperator by infinite LOCC or not, etc. Because by the definition of LOCC, you can think that all the LOCCs are separable superoperators. But what is the result about the converse? In the year 2009, this year, Eric Chitambot, he is a very good researcher in the field of quantum information theory. Maybe few people knows, many people of this basically who are doing research in this field, they know Eric Chitambot. He is doing very good research in quantum information theory. He with other people, they have published a paper that where they have provided a protocol. By this protocol, you can actually segregate the difference between separable superoperators and LOCC. Actually, their result was that not all separable superoperators can be represented through LOCC. All LOCCs are separable superoperators, but there are some separable superoperators that cannot be achieved by any LOCC. This is their main result. And later on, many people are also doing some work, but this is the first one where this difference, that is means that set of all LOCC is a subset, proper subset of the set of all separable superoperators. This is the basic thing they have published. Earlier, whether these two are equal, these two sets are equal or non-equal, there is a confusion. But now it is established that set of all LOCC is a proper subset of the set of all several. There are some other kind of operations, very important PPT preserving operations. There are some other operations, non-entangling operations. So if you go through these basic operations, you know many things and many interesting results on those theory. Actually, if you go interested in the understanding of non-entangling operations, then you find a paper by Banda Fernando and Planio. They have showed that under non-entangling kind of operations, the entanglement dynamics is reversible. So this is reversible kind of theory. Otherwise, it is irreversible in PPT preserving or LOCC or separable operations. You will take the entanglement dynamics is not reversible in that sense that you could extract the same amount of entanglement by those kind of operation, which is required for creating those kind of states. Okay. So there are many interesting things if you try to understand the basic nature of physical operations. So these are very, very much required to understand properly the quantum information theory. Now I am going to the main basic things in our lecture, that is distinguishability and indistinguishability. Now, basically, I first give you some review and give some proofs of some results. Actually, not many proofs because otherwise I cannot cover many things. Okay. The subject starts with the most striking invention by Bennett group. Well, you know that Charlie Bennett did many things for quantum information theory. There is a paper in 1999 called Quantum Non-Locality Without Entanglement. This is not the non-locality in the sense of well correlation. So it is not that kind of, but it is a kind of non-locality that is not local in that sense. Without entanglement, this happens. Now, I am giving a complete orthogonal examples of a complete orthogonal. This is actually coined by a Bennett group in their paper. What is I am not giving the here in the symbols the normalization factor. There are one normalization factor 1/√2. So you have heard this normalization factor. So you can think about 0, 0 plus 1, 0, 0 minus 1, 2, 1 plus 2, 2, 1 minus 2, 1 plus 2, 0, 1 minus 2, 0. So you can actually, you can pictographically, you can, if you give a plain picture of 3x3 then you will find it is kind of bricks in the walls like that. So it is called tiles UPV actually, not tiles. UPV is later on I will do. This is a complete basis. So there are 9 states. So that this is a complete orthogonal basis in 3x3, you can check these are orthogonal because they are in at least in one side, all the 9 states are orthogonal to each. So it is another computational basis, not the computational basis of the 3x3, and by the choice that it all are product states. Okay. Now, Bennett group has shown that in their paper that these product states are not LOCC distinguishable with certainty in the single computer. That means if this set of 9 states has taken, and if you share one state from this set to two parties, then those two parties with local LOCC, they will not distinguish which state they are actually sharing. So by bound on information theory, Bennett group proved this, and this proof is very large and long. That are actually Hardy with Walgett. They have shown taking finite LOCC case, they have proved another alternative proof of this result. Okay, so I will suggest the students that you could go through the Hardy Walgett's paper later on, by which you can actually learn how why this full basis is not locally distinguishable. But if you go through the Bennett paper, then you may be confused because this proof is very large and it contains the many information theory bound. So I suggest that you will go first the Hardy-Walgett's result, proof of this result. Okay. Now, another interesting example that is also given by Bennett group in another paper in the same year, that is the unextendable product basis. I am giving a product basis which is a complete basis. Complete, that is in 3x3, all the 9 states are there. But if you want some of the states, 4 states from this 3x3, 0, 0, minus 1, 2, 1, minus 2, 1, minus 2, 0, 1, 0, minus 1, 2, these 4 from these 9 states. And if you all have normalization factor 1 by root 2, and if you take 0 plus 1 plus 2 by root 3, 0 plus 1 plus 2 by root 3, then these 5 forms a smaller, they do not form the complete basis, but they will form a 5-dimensional system. And you will find at once that there is no other product state which is orthogonal to all these 5. You could not find. You could not find any product state which is orthogonal to these 5 states. So you need entangled states to complete the basis. So other 4 states, if you wanted to complete the basis, they should be entangled. There is no other product state which is orthogonal to this basis. So this is so you cannot extend this set of product states to a complete basis of product states. Okay, but if you drop this 0 plus 1 plus 2, this, then you find the earlier this last state, 5th state, what I have written 0 plus 1 plus 2 by root 3, 0 plus 1 by 2 by root 3, you will add there, divided by root 3 as a normalization from 1/3. This state is called stopper or blocker because it blocks the local dimensions so that you cannot actually find any product state which is orthogonal to them. And by this way, the Bennett group, they have termed this kind of product states, orthogonal product states, as unextendable. So you cannot extend unextendable product basis. And they have not given this only bipartite system. They are also given in C-qubit system, and they have given a definition of how could you find in multipartite system the unextendable product, this definition, everything what is important in all the UPVs are there, they have given a theorem in their plural paper that all UPVs are locally indistinguishable. You cannot distinguish this kind of set of states. So if you if whatever the UPV is, if you given a class of UPV and a state from this class is given to parties, then you cannot find through LOCC that which state you are actually sharing. So all UPVs are locally indistinguishable. The set itself, this 3x3 is not locally distinguishable. And not only that, after that, these results actually generates the subject distinguishability and indistinguishability aspect. Because what Bennett group shows that there is much more in information theory, this kind of things. Actually, in many problems of data hiding or some other practical questions, this distinguishability, indistinguishability aspect is very important. Many where. Now, what we have found in this non-locality without entanglement things, that there are product states, set of orthogonal product states, which is not distinguishable locally with certain. Okay. Now, quite contrary to this fact, so with this idea, you can think that if you take entanglement as a set of states, entangled states as a class of state which you want to distinguish locally, this is far more harder to distinguish. But quite contrary to this fact, what you all get in 2000, they have found that any two orthogonal pure state, whether it is bipartite or multipartite system, whether entangled or not, any two, you take a pair of orthogonal state from any composite system, which may be bipartite, which may be multipartite, so more than two number of parties there, they are always locally distinguishable with probability 1. With probability 1, you can distinguish this pair of states. So if given two states, if you all the parties are given a state from that state, then they are doing some LOCC or doing this, and after some times they will say that what state, they will assure you that what state they are sharing. Okay, this is the result. So for this result is very interesting, and it is from the mathematics part, you find that this result actually prove through a result of algebra simultaneous diagonalizability of two matrices. With the help of simultaneous diagonalizability of two matrices, this proof has been done. So any two bipartite or multipartite orthogonal state is locally distinguishable. Okay. Why? They have shown that you can actually express this any two orthogonal pure bipartites in this form. Suppose one is psi, another is phi, then you can write down 0, chi, 1, zeta. Now is this chi bar, xi bar, eta bar, they may be pure state from all other parties, but you can write, at least firstly you can write this happens. This is a multipartite system. Now in the first system you find 0, 1, 2, this is an orthogonal basis, and for our second other party, these states are written for 0, chi and chi bar, for 1, xi and xi bar, for 2, eta and eta bar. So for 3, if there are 3, then 3 some other this. Now this chi bar, xi bar, they are pairwise orthogonal. So if first party will measure projection value measure on their basis 0, 1, 2, this, then if it's projecting 0, then all other party state is chi chi bar. So these are orthogonal. So they should be, if you consider as a bipartite system, bipartite state, then this is the other party state, chi and chi bar. So you can distinguish them with this measurement. You can distinguish if you find one, then xi xi bar. If you find two, eta eta bar, and these states are distinguished by other party. So you can actually write down these are the unnormalized form of psi and phi, and normalization constant that does not require for this distinguishability. So we avoid this normalization constant. Okay. So you can always write down any two bipartite pure state. Actually, you can by this result you can actually find for multipartite state how the protocol runs. Okay. So by this way you can assure that that psi and phi are distinguishable locally. Okay. Now consider 4 Bell states. Now I am going to the basic thing of Bell states. 4 Bell states, phi plus minus means 0 0 plus 1 1 by root 2 and 0 0 minus 1 by root 2 and psi plus minus. These are 4 Bell states, everyone know. And there are many lectures where you find that about Bell states. So I understand that students should know these Bell states. These 4 states, set of 4 states, if one state is given to 2 party, then by LOCC they cannot distinguish this. So these Bell states are not locally distinguishable with certainty in the single copy case. Okay. So Sivasis and Gopusat, their group actually proved it. The proof is quite interesting because in the activable bound entangles, I will give you the same kind of proof also runs there. For this, we have coined this Smolin state. Consider a 4-qubit state shared among 4 dishes. This is a mixed state. Okay, rho 4 plus. And this plus means I will explain later. This is 1/4 of projector on 5 plus tensor product of it. This is 4 party. So P means projector on this. So 5 plus 5 kg. So these are projector on 5 plus, projector on 5 plus. Then second 5 minus 5 minus, psi plus psi plus, psi minus psi minus. Okay. Well, 5 plus 5 minus psi plus are the Bell states. What I written in their usual basis. What we have found in the earlier slide. And this P dot represents the projector on those state. Now this rho plus 4 plus state is very interesting. It is now we are called these are Smolin state, but Smolin is coined is that they unlockable, and later on this is known as activable bound entanglement. Bound in the sense if all the parties are in distance left, then with LOCC they cannot extract any entanglement from this. But if at least one pair of parties came together in a lab, then they could do some Bell measurement, and by which you can observe that in this form that other 2 parties will share a Bell state. So if this is actually separable in all 2 cross 2 cards. This is okay if they are in the distant labs. But if they came some lab, then they can extract some entanglement. In that sense, this is called bound entanglement, unlockable bound entanglement. So lock could be unlocked by coming together in a lab in that sense. Okay. So this state you can write down in this is symmetric in all respects of all the parties. This all 4 parties, this is a symmetric state. I think I would always write down in this form. So the state is symmetric with respect to all the 4 parties, separable in 2 cross 2 card, what I have said. And if any 2 parties come together in a lab, then it is possible to share Bell states among other 2 parties. Just what they will do in a lab, they will do the Bell measurement, and by which other 2 parties will share a Bell state. Okay. Now, if these 4 Bell states, these 4 Bell states are locally distinguishable, then what if you assume that these 4 well states are locally distinct, then all the parties situating in the different distant labs, a pair of parties will distinguish which pair of well state they are sharing, and correspondingly by the form they could communicate to other 2 parties that you are sharing this state. So if you allow that this set of 4 well states are locally distinguishable, then situating at different distant labs, these 4 parties can share entanglement. Earlier I have said they are separable in any 2 cross 2 card. So situating in distant labs, they cannot generate any entanglement between any 2 parties. But if you allow that well states are locally distinguishable, then any two party will distinguish what state they are sharing and communicate this result. And after their measurement, they have lost their entanglement, but other 2 parties can share entanglement, which is not possible situating in distant labs. So from the form of Smolin state, you can understand that 4 well states are not locally distinguishable. Otherwise, from separable 0 entanglement to you can create entanglement. And in quantum thermodynamics by electricity, you cannot generate entanglement. So you will actually violate that this thermodynamics of entanglement theory that through electricity you can actually generate entanglement. Here, this result proves this thing. So it is a very interesting result proved by Ghoskar et al. So this is the basic flavor of this proof. This Smolin state gives you the flavor of the proof that well states, if you allow these well states are locally distinguishable, then you can actually create entanglement by LOCC. And it is not possible. Okay. These things is in the proof of this well state. And later it is also proved by using bound on distillable entanglement that even any 3 of them are locally indistinguishable. If you take, or not taking all the 4 well states, if you take a set of 3 well states and 1 state from that set is given to 2 parties, say A and B, then they can, with LOCC, they cannot distinguish. You look at this picture. In case of 2 well states with the Hardy-Walcott result, you can distinguish, because any 2 orthogonal bipartite or multipartite state can be locally distinguishable. But if you allow only 1 single state in their set, so if you take 3 well states, in the case, this is also not possible. And with the relative entropy and entanglement, their proof is based on the relative entropy of entanglement. By with this bound, they have proved that any 3 of these well state, if you take a set of any 3 of the well state, then from this, if 1 state is given to some parties, then they will not distinguish locally which state they are sharing. Later, the result also extended to non-maximally entangled states. I also, in a paper with Aditi Ujjwal, Prasad, everyone is there. Now, the problem of local distinguishability or indistinguishability in 2 cross 2 system that are almost completely solved by Hardy-Walcott. How? In the sense that which 3 orthogonal pure states would be locally distinguishable or which 4. So in 2 cross 2, they have settled down everything. This paper is very interesting. You can go through this paper. Later, Hodicke group, they have given also large number of work in quantum. Of a for a complete orthogonal basis in bipartite system to be locally distinguishable or not. Oh, when? And they have shown that if at least one of the states is entangled, then the basis is not. That means this complete orthogonal basis is not locally distinguishable. At least one of the states. Look at this result. And the basis is probabilistically distinguishing if all are product. Probabilistically with some probability you can distinguish if all are product. So you can, not certainty, but with some probability you can distinguish a class of complete basis probabilistically, not with probability. That means with less than one probability. Okay. Now there are
Yeah, I think he has been disconnected.
Okay.
This is a common problem.
hello.
Oh, you are there. You are there.
Okay, came back. Okay.
You are using mobile phone?
No. This is a tab.
No. What I mean to say is, are you using mobile internet or Wi-Fi at home?
Oh, this is Wi-Fi.
Okay. Then to
Wi-Fi. I in my home there is Wi-Fi.
yeah, please continue. Yeah.
Yes. Okay. I'm going to the these are all I have completed. Now, Bandyopadhyay and Walgett, they have shown that that any three linearly independent pure quantum states are locally unambiguous. This is a kind of distinguishability, that is unambiguous distinguishability. I am not going to kind of things, only the basic things. Letter Duan et al. Provided a lower bound of the number of locally unambiguous distinguishable in arbitrary basis. So there are some results. Letter Walgett and Scott also give some properties with unambiguous. So there are some other aspects of distinguishability. I am not going to that aspect. A lot of things has been developed in the this local distinguishability or indistinguishability of kind of states. So many results prove many people in throughout the world, because it gives you the what I have said, that basic core things of this quantum information theory, and it has many applications on hiding secrecy and in other kind of things. Now I am going to the local discrimination of generalized basis. What does it mean by generalized basis? Now consider the full set of orthogonal maximally entangled states in D cross 2. What is the form of this state? This psi mn is 1 by square root of d, and this sum goes to 0 to d minus 1. This is expectation. Exponential of this. This you can take as nth root of unity. This quantity, this complex quantity in general, you can took out this nth root of unity. D cross D means dth root of unity. Okay, not nth root, dth root of unity. And it has formed the J plus M. This is the general form of full set of orthogonal maximally entangled states in D cross D. Okay. It is interesting to note that all these states are locally unitarily connected by a unitary operator UNM, and this UNM you can find from this form of this item and this form of this UNM. They are locally in a UNM in one side, and in other side you will do the identity operation. So all these IMN are locally unitarily connected by each of them, and you can find from the psi 0, 0, you can generate all these full bases by applying UNM tensor Y identity, where UNM is this unitary operator. And these UNMs have interesting properties that they are trace orthogonal. Actually, by such kind of result, Ghosh et al. Later resolve the basic problem of local discrimination of generalized states. The class of maximally entangled states are also known as generalized. In initial paper, I also there. Now, one may ask about the maximum number of states that are locally distinguishable with the maximum number of states in this D cross D set. You can distinguish locally with certainty in single coupling. Now, by using a bound on distribution, it is shown by Ghosh et al. That no D, I am also there in this paper, D plus 1 state from these D square states are locally. You cannot distinguish any D plus 1 from their state. Any. If you cross the number D, you cannot locally distinguish. This is done by some bound on using relative entropy. Now, let us show that if D is prime, then K states are locally distinguished if K satisfies this condition. Clearly, any 3 from the set D squared states are locally distinguishable. Then Nathanson, he is using some mutually unbiased basis, and he said that in 3 cross 3 system, any set of 3 maximally entangled states is locally distinguished. Using the existence of mutually unbiased basis, he also found the condition for a set of K maximally entangled states. He has also reproduced the result of fun. Okay. And the result of our D plus 1 state. Now, all the above results do not provide us the condition that which D or less than D number of states from D squared generalized states are locally distinguishable. Okay. To proceed further, we now go back to the teleportation protocol given by us, local discrimination. This protocol runs as follows. Now, consider an arbitrary qubit, because we have taken the D cross D. So you take an arbitrary qubit. Use any state from the whole set, all are maximally entangled state. So you can teleport this qubit, whatever the forms of this qubit, because maximally entangled state using as a channel, you can teleport perfectly. So use any state from the whole set of generalized well states. Any state as a channel, you use teleport the above qubit using the maximally entangled states as channel using standard Bennett protocol. So you will do this unitary operators, you will have to do in the side of both. Okay. Then you will find using any maximally entangled, you will find some phi. From phi, if you use the channels are different channels, the form of phi will be different. Now, what you will find that that therefore the qubits obtained after teleportation are different. Now consider any D or less than D number of generalized waves. If all the states found after teleportation are orthogonal, if all the phi after teleportation are orthogonal to each other, then you can distinguish from which channel, because they are orthogonal. So in the above side, you can do a measurement and which state they found they will come, because they all are orthogonal. So if you pick some state, then which channel they have used, they will determine. So if all states found after teleportation are orthogonal for at least one qubit phi, then the states are purely locally distributed. So it is just sufficient for condition for the local distribution. If you find all the different phi's are orthogonal to each other, then you can identify from which channel it is transmitted, and by which you can actually distinguish this number of states, which is d or less than equal to d. Okay, so they are locally distributed. It is interesting to note that the condition for existence of such phi for d or less than d state is equivalent to the finding of a solution of discriminating corresponding those unitary operators by a qubit. These two are equivalent. Now there are two observations. What if you take two copies, not a single copy, copies of whole class of generalized Weyl states, and then if you use this teleportation protocol with two qubits, different qubits, then you can show that all the d square are states are locally. So if you take two copies of generalized Weyl state, so all the d square will be locally distinguishable. But in single copy case, you will find that d plus 1 states are not locally distinguishable, and less than d or d, we have a sufficient condition with the teleportation protocol. Okay. So if a set of d or less than d states are locally distinguishable, then considering the teleported state as basis, we can rearrange the states in such a manner so that they could be distinguished by one way. This interesting thing of this teleportation principle that we are actually distinguishing them by one way LOCC. Now, what I have said, this is a sufficient condition. So in some cases, they will fail. Now we'll give some concrete examples of this teleportation protocol. Consider the following four states in simple, not the full six. Only this four, psi 0, 0. This is the form of psi 0, 0. This is psi 1, 0. This omega is nothing but the sixth root of unity. Okay. Psi 3, 0 and psi 0, 3. These four states, if you consider only these four states from 6 cos 6, so this is less than d, because 4 is less than 6. What you will find? Teleportation protocol fails for this. So if you take a qubit with this channel, the four qubit you will find they are not orthogonal to each other by teleportation protocol. So teleportation protocol fails for this stage. Also, there are many 4 cross 4, 5 cross 5. There are lots of examples we find at that time. Those states where the teleportation protocol fails. Now later, Shivasis and other people, and also from Zubro, they had some other results they have found, which actually provides when this one-way LOCC is also necessary for this kind. So if you go through the papers by Ghosh and Bandyopadhyay et al., you find almost the complete solution, which kind of states will be distinguishable by one-way LOCC. Okay. This is the result of the generalized Weyl state. Now I will provide an interesting family of bound entangled states known as activated bounded, and they have this peculiar distinguishing distribution. Consider the class of activated bound states. Firstly, I give the 4 qubit states shared between among 4 distance parties. Why? Because I have said earlier this rho 4 plus I have taken, this is the small state, and you can take rho 4 minus, then you have taken projector of 5 plus, then projector of 5 minus with him. My 5 minus with 5 plus. psi plus with psi minus, psi minus, psi minus. Similarly, you can take sigma 4 plus minus. You have taken that phi plus with psi plus minus and similarly. So all these four possibilities we will find, and these four states forms the four qubit states. All are actually unlockable bounded entangled state, or you can say as activable bounded entangled. If activable or unlockable, that same term as if you can active if some parties came together in a lab. Active, then you can extract actually entanglement. In that sense, they are activable or unlockable. Okay. You know that this phi plus phi minus, psi plus psi minus are base states written in their region, and this. And I have said already that Cryptography is the small state described earlier. The class of activable bounded entanglement in multi-qubit system constructed as follows. You can actually construct a class of activable bounded in higher dimensions. How? In any even number of qubit systems, starting from 4, there are exactly 4 states belonging to this class. A nice Bell correlation is seen in this class between the states of the two system, and that provides the generalization of the scheme. What is that? If you denote that 2n qubit states as rho 2n plus minus and sigma 2n plus minus, then the next 4 states of 2n plus 2 qubit system are given by these formulas. That's rho n 2n plus, rho n 2n minus, sigma, and for sigma plus minus, rho with you just interchange phi plus phi minus, psi plus psi minus, these 4 possibilities, then you will find all these 4 2n plus 2 qubit systems unlockable bounded. This is the form of whole class of state. By recursive way, you can actually generate all the class of activable bounded entangled states. Okay. Now the formula enables one to generate the whole class of states from 4 qubit states by recursive method. We now show some special features of this class of states. What is this feature? First feature is permutation symmetry. What is this? The whole class of states are symmetric over all parties concerned. So you can interchange the parties here and there. Then you will find ultimately the form of the state is remain invariant. That is, the states remain invariant under the interchange of any two parties. So this is the permutation. Next one is orthogonal. All these 4 in a particular 2n qubit system, or 2n plus 2, or from equation 2 of the 4 states of 2n plus 2 qubit system are orthogonal to each other. How you could find? You have actually these 4 states of the small type states are orthogonal to each other. These are very easy to prove. You can actually take as an exercise. Then by the recursive formula, you can show that all 4 are in a particular dimension, 2n plus 2 qubit. You will find the all four activable bounded strangles are orthogonal to each other. So they are orthogonality of these things. Lastly, what is the basic interesting thing we have proved? Indian is also there in this paper, that local indistinguishability problem. The 4 states of 2n qubit system, n greater than r, for any n greater than 2, you will find that they are locally indistinguishable. These 4 cannot you distinguish. How you can show for smallest kind of state, this 4 qubit system, we have proved the same line of proof given by this Go-Shuttle in their Bell state formula. Actually, if you able to distinguish these four Smolin-like states, then you can generate entanglement, which is not possible if all the 4 parties are distant, and because in any 2:2 card, all states are separate. So this is the basic things of the this activable bounded entangled state. And by generalizing this aspect, we show ultimately that if four of these, any one of these state at least, you can find that what is sharing by the parties out of the 4, which one by association only, you can actually generate entanglement. This is the basic thing. So by the thermodynamics of entanglement when all the parties are situated in different distant labs. This is a very large multi-party system also, so they cannot find any. So, we have discussed mainly this is the result we have found. Now I am giving you just to show some result which depends upon the non-locality of entanglement business. That is, this is the current trend in the research of distinguishing. Many people are doing in this business. We have discussed mainly results on distinguishing the class of orthogonal pure, especially the problem of local distribution of maximum limit. Several other results provided by recent entanglement assisted. There are some, if you're not able to distinguish them perfectly, then you can assist by entanglement. So you can give some resource by which whether you can discriminate those states. These things generate a lot of interest in this local distribution. So by assisting entanglement. Now looking back to the result of non-locality of the entanglement of Bennett group, if you consider in any multi-party system, the concept of non-locality is not fully understood, except for some completely orthogonal product basis or some unextendable product basis. Otherwise, it is not. Now, we now provide a result in tripartite system which exhibit non-locality without entanglement but are distinguishable if we provide some assistance. I am not going to do any proof because if you find the form of the class of states in that this is itself big, so I am not going to do any proof. I am showing that there are a lot of results coming on this, and now I am giving a 6 cross 6 cross 6 tripartite 6 cross 6 cross 6. There are 36 orthogonal product sets, and this is locally LOCC indistinguishable. And what I will give, they have some properties that I will discuss. This 36 states in 6 cross 6 cross 6 tripartite system is locally indistinguishable. Now, if we consider not taking this 6 is a particular case as 2D cross 2D cross 2D, then we actually find 18 into D minus 1 orthogonal product states cannot be perfectly distinguished by the system. Okay. If you take, in this case, I have taken in theorem 1, D is odd. You also take D is even, then the form of the state is different, and I will find that they are also not perfectly distinguishable. Something is missing here. Now, if you consider the odd dimensions, C2K plus 1, 2L plus 1, 2M plus 1, then this set also cannot be. There are actually 6 into this, all these number are there, K plus L plus M minus 5 orthogonal product sets cannot be perfectly distinguished by LOCC. This number have many things. If you take one even dimension, other two are odd, then you will find this number of orthogonal product sets cannot be perfectly distinguished by LOCC. We will have, if you take 2 of this is also not, okay. In this, if you take all these are even dimension but different, then also you find this number of orthogonal product states. They are not called. Now one may observe that each class of product state constructed above, they are not UPB. What we have given, they are not UPB. They are some other kind of product business. The sets can be, they are actually computable. Okay. The sets can be extended to orthogonal. All, but they are not, apart from this, they are not locally distinguishable. They are smaller sets. All the set of sets cannot be perfectly distinguished by LOCC. This is because of the fact that locally it is necessary to eliminate some states in a given state, which is not possible in this given. What we have given, you cannot actually eliminate any state from this locality. The speciality about all the theorem is that they are LOCC distinct set containing this number is there, containing minimum number of states with respect to their dimension. What we have considered these numbers coming as a minimum one. Okay, you can go beyond that number, but below that you cannot find any set of product state which is locally indistinguishable. Okay, this is the main thing. Because of the symmetric structure of the state, it indicates that no one of the three parties cannot eliminate any state from the states. Now, if you want to distinguish this class of states, then entanglement is required. This is a tripartite state. By Bell state, many people have done many results. But in tripartite case, there are not many results. We shown that only one copy of GHZ state is sufficient to distinguish this 36 state. What I have, what we have shown that these 36 orthogonal product states can be distinguished by LOCC only using one copy of GHZ state. Not only that, if you take this dimension where D is an odd or even, the set of 18 into D minus 1, orthogonal product set can be distinguished by taking only one copy. It is not the case that for 6 cross 6 cross 6, you take only a GHZ state, but it is also for, it is irrespective of dimension. One copy of GHZ is sufficient, and this amount of entanglement is sufficient to distinguish those class of orthogonal product states. If you take the odd, then also you can three parties is sufficient the product state by LOCC. Only a GHZ state shared between three parties, then also this. Since all the states are symmetric, it is really not important which pair of parties holds the resource state. Also, the requirement of entire resource to accomplish the task of distinguishing the non-local set does not depend on the dimension of the subsystems. It is also to be noted that all the LOCC indistinguished sets constructed are minimal in cardinality. Also, the above class of states are minimal sets which are distinguishable through GHZ state. We observe advantage of using genuine entanglement as a resource for distinguishing those class of states. Here I have given two interesting open problems. The first one is to find the LOCC indistinguishable sets of lesser number of states for arbitrarily high dimensional multipartite quantum systems. Okay. What is the lesser number of states for which arbitrarily high dimensional? This is one open problem. Second one, the question of optimality of the entanglement. Actually, GHZ, it is optimal. Below that, you cannot do. This question remains very good, and this is a kind of research many people are thinking, which is the optimal resource you can use to discriminate as an entanglement assisted protocol. Okay. So this is also given. Some other things also there in a given universe space. The subset constructed here as small state. This is the number of state contained in the set is much lesser than the net dimension of it. Hence, an essential research in this direction is to find out the number of orthogonal products from which no one can be eliminated by orthogonality preserving. But this is a kind of measurement. You can also think this is a new kind of operation. People are using explicit construction of such are also important for any multipartite. So in multipartite quantum system, there are a lot of problems you can actually try to resolve for distinguishability aspect. And also in bipartite system, there are also some problems, but what I am showing that this multipartite business is quite open. There are some references. Okay, just a list of reference I have tried to give. In this case, my student Adu helps me a lot. Okay, thank you to all for your patience. I am completing my lecture.
Okay, thank you, Devashita. You can stop presenting now.
Yes.
So generally, if there are questions, then they will put in the chat box, but looks like there are no questions here. So let me open it to the audience if anybody wants to ask a question.
So looking at the only the slide, asking question is very difficult.
Yeah, Devashis, I have a question.
Yes.
See, the one which you showed that things which were not locally distinguishable, with one GHZ state, it can be distinguished.
Yes.
Can that be used for something like cryptographic protocol? Because if
yes, actually, this indistinguishability nature you can use in many cryptographic protocols. This is the main area where cryptography or data hiding, this kind of area, this indistinguishability nature is used in these practical problems of quantum information theory. So many people are interested distinguishing indistinguishable from those information theory perspectives. There are many results. And you know that Andreas Winter and their people, they have generated a theory, data hiding, quantum data hiding, that requires basic requirement on that quantum data hiding, the state should be indistinguishable.
Right. Now, this another question, these bound entangled states.
Yes.
They are also very close to separable states, right?
Yes. Many times. But these unlockable bound entangles, they have very good number of entanglements, because you can actually, if two parties come together, you will actually find a Bell state. So these unlockable bound entangles, they have good resource. They are good resource. Actually, by them, this activable kind of thing. So what first give by Peter Storer and the people, they in a paper in 2008, this activation of entanglement, they have used this knowledge state. In 5-party situation, they have shown that this activation will be done.
Now, just like, this singlet and triplet, we have physical examples, like Bell state at least.
Yes.
Similarly, for these bound entangled states, are there any physical example one can think about? I don't understand, what is this bound entangled states physically?
Physically, what you understand that in some sense, this is some state, this is some correlation that is preserved by the structure itself. Because you require some entanglement to create this kind of state. So this is like bound energy in general physics. You can compare bound entanglement, because entanglement is resource in quantum information theory, and you can compare entanglement with energy in general physics. Then this bound energy things is comparable with the bound entanglement concept. Physically, this is the main motivation of bound entangled state.
Okay, thank you. Yeah.
Any other question? Okay, we're almost like end of time.
Yes.
Yeah. Okay, if not, then let's thank Professor Devarshi Sarkar once again.
Thank you.
Thank you very much.
Okay, thank you. Okay, Chiranjeev,
thank you.
After many days,
I think more than 2 years. 2019 we met when you came here.
We have met. Yes. Okay. Keep safe. Keep safe from the COVID. Okay. Thank you. Okay.
Prashant.
Yeah.
Okay, Prashant. Thank you. Okay.
Prashant, I'll leave now. I have to go to the lab.
Okay. Yeah.
Thank you.